Welcome to our Nielsen Fitness in-home certification. This is our weight loss course, and we will be focusing on Module 1 today. Module 1, the matter of it all. The purpose of Module 1 is to understand the foundation of weight loss. Why do we need to know the foundation? Once you have a solid foundation, you will be able to effectively help multiple different clients despite the obstacles in your path. A lot like baking a cake, once you understand the foundation of how a cake is made, you can make substitutions, you can pick different recipes. This allows you to pick the most effective recipe, and you can design that cake and customize it to how you like. This module focuses on the why effective diets work. A lot like building a cake. What are the best diets for you or for your individual client, and why they are effective? Once you know why they're effective, you can see what is going wrong and fix any mistakes or anything you're going from there. Going back to the very basic science of it all, what is our body made of? Almost 99% of the human body consists of 6 main elements: hydrogen, oxygen, carbon, calcium, and phosphorus. All these elements form complex molecules that are held together in a magnitude of combinations by chemical bonds. Most of these bonds require and hold energy. Simply put, how our body weight changes by adding or subtracting these elements and absorbing or releasing energy. Where does this matter come from? Unfortunately, we cannot synthesize matter from nothing. The physical matter and energy must come from somewhere. To gain 10 pounds of mass, we must consume 10 pounds of mass. Not all that 10 pounds that we consume is absorbed, so we're not 100% efficient. Not all food we eat goes right to our hips. Depending on the source of it, what it is, that will let us know how much we're going to gain. Our bodies are amazing things and can form various molecules in if the right material is present, and of course, energy. So hydration is important to pay attention to, but we're not going to focus in too much detail on this. It can be affected by fluctuations in sodium intake, glycogen levels, creatine, all that kind of stuff. So we're not going to go into too much detail because we don't want to fluctuate these areas too much. We want to be in optimal sodium saturation, optimal glycogen saturation, and optimal creatine saturation. We're not going to try and manipulate our weight with hydration unless it's for specific sports like boxing or other sports that require an actual weight. The focus is going to be on body fat and maintaining a healthy body weight based off of losing body fat rather than just kind of dehydrating yourself by sitting in a sauna or anything like that. Where does the matter go? The byproducts of various chemical reactions in our body will be recycled or excreted. We excrete them through defecation, urination, or exhalation, and the energy will be transferred or released as heat. To lose 10 pounds of mass, 10 pounds of something must be excreted, one way or another. More specifically, where does the fat go? So fat plus oxygen goes to carbon dioxide, water, and energy. Once it goes through fatty oxidation, we can follow the carbon chains and see that we exhale carbon dioxide, we urinate out H2O or water, and we release energy as heat. And this is where that fat, as we use it, as we burn quote-unquote energy, this is where it goes. Again, how do we form all these complex molecules? We use energy to bind all these elements together, creating complex molecules in a functioning human body. The law of conservation of energy states that the total energy of an isolated system is constant. Energy can be transformed from one form to another, but can neither be created nor destroyed. When we are at energy balance, body weight will stay the same. When we're in energy surplus, body will store that extra energy as fat, weight will increase. And when we're in energy deficit, our body will dive into our energy storages and weight will drop. Adenosine triphosphate. ATP is our body's currency of energy. This is how we transport energy from reaction to reaction. An adenosine molecule bonded to a 3-phosphate chain. In between the phosphates, there's strong high energy bonds. This holds all that energy in. When we break these bonds, we release it or absorb that energy from reaction to reaction. An example is during a muscle contraction, we utilize the energy from ATP between those phosphate bonds, and we use this to change the shape of myosin, allowing it to contract and perform that power stroke. During exercise, that energy is released as heat, and that's why we heat up when we exercise or resistance train. ATP is a very dense molecule, and this is why we don't store all our energy as ATP. It would be way too dense and wouldn't be able to utilize all that energy just to move around. So alternatively, we store energy in the form of fat. Most of the reactions in our body require energy and is very essential for life. Because energy cannot be created or destroyed, our body must absorb it. We absorb energy and transfer it from task to task via ATP. When excess energy is consumed, we do not waste it, we store it in our body as fat. We are very good at storing energy and very efficient creatures. This is some of the reasons why we're at the top of the food chain. Now the next question is, how do we store this energy and where does it come from? Before we dive into fat storages and energy storages, we need to understand the metabolism. So when we're talking about metabolism, we mean the sum of chemical processes existing in the living human body. We call these biochemical reactions. We have two types of biochemical reactions. We have catabolic reactions, reactions that release energy, or exergonic, and we have anabolic reactions, a reaction that absorbs energy, or an endergonic reaction. Catabolic reactions break down molecules into smaller molecules. During catabolic reactions, energy is released. An example is the breakdown of glucose during glycolysis. The 6-chain carbon molecule glucose is split into 2 3-carbon molecules called pyruvate. Energy is released and conserved in the form of ATP. This ATP can be transferred through the body and used for certain tasks such as anaerobic activity. Anabolic reactions bind molecules together to form more complex molecules. These reactions absorb and require energy. An example is the formation of a triglyceride. When a 3-carbon glycerol molecule reacts with 3 16-carbon fatty acids, ATP is absorbed and required to form these ester bonds. A 51-carbon triglyceride is formed. In real life, we see 16-carbon molecule fatty acid chains, we see 18 molecule fatty acid chains, and sometimes 20. These are the most common forms. These are variations in the fats. Back to our question, where does the energy come from? We consume our energy through our diet. Energy must be consumed due to the absence of chloroplasts. We're not plants, so we cannot perform photosynthesis and get energy from the sun. Mostly we consume our energy in the form of food or drink. Energy-rich food and drink contains macronutrients. Some energy cannot be absorbed, such as fiber. So if we backtrack all the way, photons from the sun get absorbed through photosynthesis into the plants. Animals eat plants. We eat plants and animals. We get the energy from them. Fats, carbohydrates, and proteins are our main sources of energy. These are our macronutrients because we require them in large quantities. Compared to our micronutrients, which are not really focused on energy, they're more for vitamins and minerals and essential for other things in life. But when we're talking about weight manipulation and energy, we really focus on those macronutrients. When fats are consumed, they're broken down into triglycerides and further broken down into fatty acids, which then can be absorbed and transported through the blood to the adipocytes or the fat cells. This is the most efficient source of energy. So per gram, we we have 9 calories. Excess will be stored as fat and utilized when needed. We use this in our slow energy systems or our aerobic energy systems, so it takes time to build up, but these are our longer term energy storages. These activities like walking and breathing and daily functions, this is where we use our fat. When we consume carbohydrates, we break them down into simple sugars and absorb them into the bloodstream. Not as efficient as fats, 4 calories per grams, and excess glucose will be stored as glycogen in the muscle or the liver. When glycogen storage are fully saturated, the excess will be converted into fat and of course stored as fat. Our glycogen capacity is dependent on exercise level and style, genetics, and daily habits. The fitter we are, the more glycogen we're going to store. The more anaerobic activity we perform, the more glycogen we can store. The more muscle mass based off of genetics or again exercise and activity, the more glycogen we can store. Glycogen is used in a fast energy system, an anaerobic energy system, and is meant for short-term storage. So fats are going to be more of our long-term storage for energy. Glycogen or glycogen storage are going to be our short-term. When proteins are consumed, they will be broken down into amino acids, absorbed into the blood, and used to build muscle tissue, enzymes, transporters, and other important proteins in the body. Excess protein will be stored as fat. In a shortage of glucose, protein can be converted into glucose via gluconeogenesis and used as that short-term energy. Especially for our brain can only run off of glucose. Fats cannot cross that blood-brain barrier, so this is why we convert that protein into glucose. There is ketones that our body can use, but that's a different topic. We'll talk about that later. Again, protein is about 4 calories per gram because it will be converted into that glucose, so you kind of get that. It is very important to consume adequate amounts of protein to help maintain muscle mass and develop the other vital proteins in the body. One important macronutrient you should probably not cut out or drop if you are trying to diet or anything like that, because we cannot synthesize essential amino acids, so we do need to consume them through food. There's no real storage for essential amino acids apart from muscle. So again, make sure you look at your protein amino acid profile. Okay, that's very important. Especially if you're a vegetarian or vegan, you need to make sure you're consuming complete proteins and getting all your essential amino acids. So we can build proper muscle tissue, enzymes, transporters, and all that other good stuff. When consuming not a full, complete protein, we might not be able to build muscle tissue, and these excess amino acids will be stored as fat, which is not what we want. To sum up, fats will be broken down and stored as fat or used for aerobic activity. Carbohydrates will be broken down and stored as glycogen or used for anaerobic activities. Once glycogen is fully saturated, carbs will be stored as fats. Protein will be broken down into amino acids and used to build essential proteins in the body. Going a little deeper into how we store energy. The main ways we store energy are triglycerides, glycogen, phosphocreatine, and sometimes protein. A triglyceride is a glycerol molecule attached to 3 fatty acids. The energy is stored between the bonds of the carbons in the fatty acid chains and between the glycerol and the fatty acids as ester bonds. Triglycerides are stored in adipocytes, so fat cells. Typically, we do not increase the number of fat cells in our body, we just increase the size of the fat cells. So by increasing the number of triglycerides, this increases the size of the adipocytes. When needed, the fatty acids are cleaved from the glycerol and transported through the bloodstream into the mitochondria in the target cell. It then goes through beta oxidation and transfers the energy through several processes to create ATP. Glycogen has a protein core called glycogen surrounded by chains of glucose molecules. This is how we store excess glucose, mainly in skeletal muscle and the liver. The energy is stored within the glucose molecule and released when it is split by glycolysis. This transfers that energy to ATP and then again goes through the body to use wherever needed. Phosphocreatine is a phosphate and creatine molecule that store high energy phosphates. These high energy phosphates are transferred to adenosine diphosphate to form adenosine triphosphate. It is used when energy is needed fast. It is stored in the muscle cells. So this is for our explosive activities like sprinting or Olympic weightlifting. Very quick, needs that energy really fast, and it's used up really fast as well. Saturations of phosphocreatine depend on, again, athletic performance and activity. So if you're training for sprinting or if you're training for Olympic weightlifting, you probably have higher saturations of creatine. We can consume creatine from some animal proteins and also in supplement form. Lastly, our protein is another storage of energy. It's not a main storage, but it does contain energy and can be utilized. In conditions where energy is not coming from glycogen or triglycerides, protein will be broken down and used for energy. Excess protein will be converted and stored as triglycerides. This is not ideal. We do not want to break down our muscle mass in most situations. It's a bad thing, but it does happen when needed. To recap, energy in excess. Fats will be stored as fat. Carbohydrates will be stored as fat as well once glycogen are fully saturated. And proteins, any excess will be stored as fat. So everything in excess, our body will convert it and store it as fat. Now that we understand the deep science behind energy and weight manipulation, we can zoom out and look at the broader perspective. So we have energy intake and energy expenditure. Our energy intake consists of food and drink intake, while our energy expenditure, the amount of energy we release, consists of our basal metabolic rate, so the amount of energy required to perform living bodily functions. The thermal effect of food, so there is energy required to break down that food so we can take that energy from that food. And physical activity, which is exercise, and our NEAT, our non-exercise activity thermogenesis, which is, again, walking around, moving around, any physical activity that's not planned or not exercise per se. When looking at the anecdotal information we have, we see that active individuals that don't eat a lot are usually leaner and have lower body weights. Inversely, people who eat a lot, especially calorically dense foods, and are very sedentary, they are usually larger in body weight. The average sedentary person ages, they gain weight. This aligns with information above quite accurately. If we look at the physiques of athletes in sports with high levels of energy expenditure, such as soccer, swimming, marathon running, bodybuilding, all that kind of stuff, we find that they have lower body fat percentages compared to the average individual. So increase in energy expenditure results in lower body fat percentages. We also see fluctuations in body weight and body fat percentage when high levels of energy expenditure stop. So a soccer player in the off season will put on 5 to 10 pounds. A famous rugby player who is retired does not look like a rugby player anymore in most cases. And again, this aligns with what we've been covering with energy balance. We look at most professions that require, a physique that is very lean or low body fat. We see models. If you ask any model, I'm pretty sure they say yes, they don't go on a McDonald's 5,000 calorie diet to get ready for their modeling. They eat less, they move more, and they eat less, and this reduces their body weight and body fat. If we look at bodybuilders, when it comes time to get stage ready, they're reducing their calories, they're increasing their exercise. They're definitely not eating more and moving less when it's time to get shredded for the stage. Seems like common sense, but you'd be surprised. And to sum up, anecdotally, it seems pretty obvious that in order to lose weight or decrease body fat, we need to move more and eat less. As simple as that. Now let's get into the science of energy balance. So anecdotal information can only take you so far, and it can be used with science to prove a point or get across a theory. So if we look at the sum of all research done on weight loss, it is very clear that in order to successfully lose weight, an energy deficit must be present. Starting with caloric restriction. In this study, 24 healthy men were put on an 8-week caloric restricted diet or a caloric balanced diet. So the experimental group versus the control. At the end of the diet, the experimental group, the calorically restricted group, had a significant amount of weight loss compared to the control group. This concludes that healthy men, if they restrict their calories, they can lose significant amount of body weight. Now let's see what happens when we control energy expenditure through exercise. In this study, they observed obese females randomly assigned to either a control group, a training group, or a training and detraining group. The organization of exercises was 10 to 12 full body exercises 3 times a week with gradual progression and an interval circuit style. They found after 10 months that the training induced a long-term negative energy balance and a sustained reduction of body weight and fat mass was seen. Also improvements in endurance and muscle gains. We conclude that exercising with high intensity 3 times a week can lead to a significant weight and fat loss. We have seen weight loss from a decrease in energy intake, and we have seen weight loss from increasing energy expenditure. Well, what method works best? Vardy and authors put 60 subjects in 4 groups. One was an exercise group, one was a caloric restricted group, one was an alternate day fasting group. When on alternate fasting days, 75% of calories were restricted, and the fourth was a control group. All 3 experimental groups were designed to create an energy deficit after 12 weeks. Each group, besides the control group, lost a decent amount of weight. No significant differences between the groups, so there was no real differences in weight loss, besides, of course, the control group. The protocol wasn't very strict, and it was designed to lose about 5%. But at the end of 12 weeks, they recorded roughly 1% loss averaged over the 3 groups. Despite the method, all 3 types of protocols produced pretty equal fat loss via energy deficit. Now let's see what happens when we compare exercise versus exercise and dieting. Van and authors found exercise plus restriction had faster weight loss. When combining both exercise and dieting, a greater energy deficit is produced compared to just exercise alone, leading to faster and more weight loss. What if we compare dieting and dieting plus exercise? Kempen found that when comparing a caloric restricted diet to exercise plus a caloric restricted diet, exercise plus diet lost significantly more fat than dieting alone. The energy expenditure recorded was significantly lower in the diet plus exercise group, leading to more fat loss than the diet group alone. Adding on exercise to a diet program is beneficial for fat loss because it creates a greater energy deficit. Now let's see what happens when we compare diet versus diet plus exercise, but control for the energy expenditure. To see really, is it the exercise and the dieting, or is it simply the amount of deficit we obtain? In 2007, Strasser and authors compared 2 types of calorically balanced fat loss program in 20 women. It was a diet group and a diet plus an exercise group, and they compared fat loss. It was an 8-week long study, and they found that there was a significant decrease in body mass and fat after the 8 weeks, but there was no significant difference between diet or diet plus exercise when calories were equal. The authors concluded that energy deficit was responsible for the weight loss, independently of the choice of method. So when we control for energy expenditure, we find that it is the deficit that is responsible for the weight loss. Despite of what method you want to choose, if you want to diet harder or diet moderately and exercise, or exercise harder, it is the amount of energy expenditure that's going to give you the result. In 2009, authors studied the effects of exercise on lean sedentary, lean trained, and obese sedentary when in an energy balance. Okay, so they all had the same amount of energy balance. They controlled energy intake by providing diets for each subject and making sure they ate everything given and no more. Okay, they were in a whole calorimeter test room so they could measure all the energy, so very accurate, very cool study. They measured everything they were burning, from NEAT to exercise to getting up and walking to the couch, to breathing. All the calories burned were recorded in that room. They stayed in that room for 24 hours. Everything they consumed was recorded, so they knew exactly how much energy was coming in and coming out. Okay, very cool study. On the exercise day, the energy intake was increased to meet the expenditure during exercise. The results showed no significant difference of fat loss between groups. The authors concluded that exercise does not result in a negative 24-hour fat balance when 24-hour energy balance is maintained. And this is independent of training status or obesity. So if you're overweight or underweight or trained or untrained, it doesn't matter. If you maintain an energy balance, you're not going to gain or lose fat mass. Let's compare low-fat diets to low-carb diets and see the long-term effects. In 2009, Brinkworth and authors randomly assigned 118 adults to either an energy-restricted low-carbohydrate group, which was about 4% carbs and 61% fat, or an isocaloric, so equally calorically dense, low-fat diet, 45% carbohydrates and 30% fats. After 12 months, on the diets, body composition and weight was measured. They found similar weight loss in both diet protocols, resulting in the conclusions that despite the macronutrient composition, as long as you maintain an energy deficit, you're going to lose a similar amount of weight. Berkey and authors found that weight loss can be achieved on a vegetarian diet as well as a standard omnivorous diet. They found no significant differences were found between both diets after 18 months. The only difference between diets was the removal of animal products, and both diets were focused on achieving an energy deficit by lowering the food intake. This concludes that you can eat vegetarian and still lose weight, and you can have an omnivorous diet and still lose weight, as long as you're in the presence of an energy deficit. Pushing into the extreme end, we look at detox fads, and Klein and Kiat performed a review of the literature on detox fads in 2015. And this goes anywhere from the master cleanser, lemon detox, so drinking lemon water basically every day and that's it, to the liver cleaning diet. Okay, so very extreme, very low calorie diets. The authors had trouble finding any reputable evidence and concluded that more evidence needs to be present to support any of these claims. Also, that short-term weight loss may be obtained through these diets. So potentially, this could lead to binging and more weight gain in the future. So getting into those really low calories, low energy deficits will lose weight, but are not healthy and not maintainable. They also found some potential health risks that come with these detox fads, and the diets actually may be dangerous with no evidence showing of detoxification. Our livers are, made to do that kind of thing. Wrapping it up, these diets do have a low caloric intake for a short period of time, despite the method, producing an energy deficit and leading to weight loss. Although they're probably not safe and definitely not recommended or effective for long term and can potentially lead to gaining more weight in the long term. To wrap up the literature, we have a 2020 review of lifestyle intervention programs on weight loss and maintenance in obese adults, concluding that caloric restriction is an effective way to promote weight loss up to 2 years. They found that weight loss wasn't maintained on average after 2 years due to the drop-off rate and lack of long-term research. So not a lot of research past 2 years because it's very hard to maintain these low caloric diets for a long period of time. Not everyone wants to stick to a low carb diet or a low fat diet or exercising every day. It doesn't work for everyone. The authors concluded that additional evidence is needed to determine longer maintenance. This shows that when on a diet restricting calories for an energy deficit, weight loss can be achieved and maintained for at least 2 years. Today we discovered that there are various methods of weight loss programs that can all be effective methods for weight loss and fat loss, as long as an energy deficit is present. As simple as it is not easy to execute and maintain. There are various methods of resistance that our body throws at us, making this weight loss very difficult despite the simplicity of it. We'll cover a lot of these resistant methods in Module 2. In the end, it is our job as fitness professionals to find the right combination of methods that are effective at inducing and maintaining weight loss for our clients on an individualized level. We will dive deeper into these methods in future modules.